Hello and welcome for another technical video from Sumitech Turbomachinery Solution. My name is Patrick and I am here to present the knowledge a machinery engineer should have on couplings. In a rotating machinery unit, most of the cases, it has been found that very less attention is given on this piece of component. Our effort is to create this video as much as indulging for all levels, beginner to senior machinery engineers. So, let us deep dive into the topic. A shaft coupling is a mechanical component used to connect two rotating shafts, typically a drive shaft, motor, steam turbine or a gas turbine, and a driven shaft, a pump or a gearbox or a compressor or a generator, to transmit power. As the name suggests, a rigid coupling permits little to no relative movement between the shafts. Once a rigid coupling is used to connect two equipment shafts, they act as a single shaft. Rigid couplings are used to transmit torque in high-torque applications such as large turbines and gearboxes where slip in coupling is not desired. A flanged coupling, also considered as rigid coupling. Gear coupling transmits very high torques. Transmits torque through splines. It accommodates misalignment by clearance between splines. It requires regular lubrication. Grid-type couplings have following features. They transmit torque through spring set between splines. Spring provides torsional resilience, accommodate misalignment, axial sliding, and bending of spring. They require regular lubrication. Jaw-type coupling have following features. Transmits torque through compression of rubber or plastics, accommodate misalignment by elastomer deformation / sliding. No lubrication needed. Elastomer wears out. Needs regular spares. Elastomers limited in temperature, oil resistance, etc. Usually lowest cost, but limited power capacity. They provide some torsional resilience. Tire-type coupling have following features. Transmits torque through shear of tire wall, accommodates misalignment by deformation of tire. No lubrication needed, can wear out, and need spares. They provide some torsional resilience, but they are not suited to high speeds. Pin-bush couplings have following features. They transmit torque through pins. They accommodate misalignment by elastomer bush deformation and sliding. No lubrication required. Bush wears out. Needs spares. Not suited to high powers or speeds. Rubber block type coupling has following features. Transmits torque through compression of rubber blocks, used mostly for low speeds for torsional resilience, accommodates misalignment by deformation and sliding of blocks. No lubrication needed. They can wear out. Requires spare. Designs can be torsionally tuned by changing the hardness of the rubber blocks. Disc pack / shim pack couplings are normally used in oil and gas and refinery as identified as non-lubricated coupling. They are API-compliant couplings. They have following features. Transmits torque through thin membranes, accommodates misalignment by deformation / bending of thin membranes. No lubrication. Should not wear out. In normal use can be used from low kW to highest powers and speeds. Reduce maintenance, easy to fit, reliable, infinite life. Low loads on bearings, low induced vibration, safe to operate, wide operating envelope, no backlash. A diaphragm coupling is a flexible mechanical device used to transmit torque between two shafts while accommodating misalignment through the elastic deformation of a thin, flexible metallic membrane. These couplings are ideal for high-speed, high-power applications and are designed for long, maintenance-free service life. Quill shaft couplings do not permit any relative axial movement between the coupled machines and normally used in power generation systems. Both are API compliant. This slide shows other types of coupling using in industry on specialized cases such as cardan shaft / universal joint, which is used normally with diesel or gas engine driven pumps. Fluid coupling where a mechanical soft start requirement is mandated. Over-torque slip coupling to protect shaft line for over-torque. Hull-set type coupling to lower torsional stiffness to tune torsional vibration. Torsional resilient type coupling, Geislinger coupling are normally used in diesel / gas engine. Generator set to counter torsional ripples to protect shaft line from high twist. These couplings are used in specific application and not API compliant. Mechanical type fuse couplings are used to protect the shaft line from sudden high torque, such as for the event of short circuits, breaker reclosure, OT negative power supply from generator during a trip. These couplings are equipped with shear pins which are supposed to fail at neck area that is smallest cross-section of the pin as shown, thereby protecting the drive. Anti-friction bearings are provided to secure the components during shear pin failures. Reduced moment or close-coupled couplings are high-performance, specialized drive components used in high-speed machinery, like turbo compressors and pumps, to minimize overhung mass, journal loading, reduce bending moments, and handle misalignment. They position flexible elements closer to bearings, reducing bearing loads and improving rotor dynamics. Many electric motors with sleeve bearings have no thrust bearing and rely on electromagnetic forces to center the rotor. The axial alignment with limited end float coupling is designed to prevent damage to the motor bearing shoulders. If required during initial design review with hydrodynamic bearings, the end float limitation is to be included for coupling supplier. Snapshot of sample coupling drawing mentions the limited end float in coupling. We are not promoting the make of the coupling using the snapshot. Disc pack couplings membrane, axial deflection stresses. Maximum stress occurs in areas where the discs are wrapped around the curved element washer. Tensile stress on top surface. Compressive stress on bottom surface. Midspan and edge stress are relatively unaffected by axial misalignment. Angular misalignment stresses. Stress occurs in areas where the discs flex around the curved element washer. However, the tensile stress and compressive stress alternate as the coupling rotates. Midspan and edge stress are relatively unaffected by angular misalignment. Angular misalignment stress cycles from tension to compression once per revolution in the shim pack decides life of the coupling. Transmission coupling calculation is a multi-step procedure centered on determining the design torque to ensure the coupling can handle both steady-state loads and operational spikes. Calculate the torque applied to the coupling based on the driver power and operating speed. Then select a safety factor, service factor, based on the application type, including factors for shock loads, driving machine type, and duty cycle. After this, multiply the nominal torque by the service factor to get the required design torque. For disc pack couplings, membrane mean stresses include the torque-induced stress, centrifugal stress, and axial compression or tensile stresses. Alternating stresses are typically given as a function of angular misalignment but can include torsional oscillations as well. When using a modified Goodman diagram, API 671 requires that the safety factor should not be less than 1.25. A sample pictorial view of installing spacer-type coupling is provided. It is very important to measure the DBSE distance between shaft end after the driver motor magnetic center is finalized and ensured that it matches with etch mark provided by motor supplier. It also important ensuring coupling hub faces are flush to shaft. Face axial runout is checked to enable proper fitment of spacer. Once the spacer is fixed, then alignment of shaft line can commence using reverse dial gauge method. A keyed connection will provide a positive stop until failure, whereas a keyless connection could allow slippage between the two mating parts. A keyless connection can transmit more torque than a keyed shaft due to more shaft surface contact. For precision meshing requirement, backlash may cause severe damage. Modern turbomachinery rotors are fitted with hydraulic taper bore coupling hubs. Coupling hubs must grip the shaft tightly. This gripping is accomplished by advancing the hub on the tapered shaft a specified amount. To facilitate this advance, one must expand the hub bore. When hydraulic pressure is used, a few specialized tools are needed. Basically, they are an installation tool, a high-pressure oil pump with pressure gauge, and a low-pressure pump with pressure gauge. To ensure satisfactory performance, the following procedure is recommended for proper installation when using the hydraulic pressure method. Step 1. Check for proper contact. Tapered bores shall be checked by using the plug gauge from a matched plug and ring gauge set provided by the purchaser. A light coat of bluing shall be used for the check. Tapered bores for keyless, hydraulically fitted hubs shall have at least an 85% blued fit surface contact to the taper gauge. Improve the contact. If less than 85% contact is found, the shaft and hub should be independently lapped using a ring and plug tool set. Clean the lapped surfaces. Remove all traces of lapping compound using a solvent and lint-free towels. Immediately afterward, spread thin oil on the shaft and hub bore to prevent rusting. Recheck the hub to shaft contact. Exercise safety step 2. Mount the hub on the shaft just as a start and mount the installation tool. Wet the threads with thin oil and rotate the tool until it butts against the shaft shoulder. The last few turns will require the use of a spanner wrench. Connect the hydraulic lines. Connect the installation tool to the low-pressure oil pump. Connect the high-pressure oil pump to the hole provided either in the center of the shaft or on the outside diameter of the hub, depending on design. Loosen the pipe plug of the installation tool and pump all the air out. Retighten the plug. Both pumps must be equipped with pressure gauges. Advance the hub to the start position. Through pumping the low-pressure oil pump. Continue pumping until the hub advances a set distance beyond the start position. Exercise safety step 3. Expand the hub. Pump the high-pressure pump. As the pressure increases, the hub will tend to move off the shaft. Prevent this movement by occasionally increasing the pressure at the installation tool. Check for oil leaks. The hub should not be advanced on the shaft if leaks exist. If the pressure drops, remove the hub and replace the O-rings. Advance the hub. Increase the pressure at the installation tool, and the hub will advance on the shaft. If all the previous steps were observed, the pressure at the high-pressure gauge will gradually increase as the hub advances. Do not allow the pressure to exceed value prescribed in manual. Seat the hub. Very slowly, release all the pressure at the high-pressure pump. After that, release all the pressure at the installation tool and remove it. Secure the hub. Remove the split collar from the shaft and install the retaining nut, but do not over-tighten. Secure the nut with the set screws provided. Shaft couplings connect the drive and driven machine, installed in between them. These units are also balanced by the manufacturers. There are different balancing methods for shafts intended to be used as a shaft hub connection with a key. The distinction is made between half-key balance and full-key balance. In order that the balance of the shaft and that of the coupling are compatible, the respective key convention must be considered for balancing the coupling. For the half-key balance, the machine shaft is balanced with an inserted half-key or before the keyway is machined. In this case, the coupling will also be half-key balanced. For this, the coupling subassembly or the coupling component is drawn onto a fixture shaft and balanced with a filled keyway. The keyway can either be filled with a half-key or the coupling is balanced prior to keywaying. The latter is the more common and easier method because the exact location and weight of the key must be known when balancing with an inserted half-key is performed. ANSI/AGMA 9000C90 and later revisions like D11, Class 9 is a standard for flexible coupling balance, primarily focusing on managing potential unbalance resulting from manufacturing tolerances, clearances, and assembly, rather than just residual unbalance. It defines acceptable limits for the mass center displacement from the rotation axis. Class 9 is a commonly specified, higher quality balance grade, frequently required for industrial machinery and often mandated by API. API 671 American Petroleum Institute Standard, Special Purpose Couplings for Petroleum, Chemical, and Gas Industry Services. Coupling balancing procedure highlights are following: balancing machine. A high-precision balancing machine must be used. Tolerance calculation. Unbalance is often expressed in terms of mass displacement, ensuring the coupling center of rotation does not deviate excessively, typically within 0.05 millimeters or 0.002 inches from the machine's rotation axis. Mandatory requirements. For applications exceeding 3,800 revolutions per minute, API 671 compliance is generally required. When the rotating equipment have high vibration during commercial operation, there are many kinds of root cause to resolve the high vibration issue. And, in case of large rotating equipment, it is not easy to perform the completed train test with job coupling and driver at manufacturer's shop. Then, the high vibration by unbalance, which was not occurred during shop test, can be experienced during commissioning due to construction and assembly tolerance and actual operation condition. In order to avoid the critical operation under rotor imbalance condition, is it possible to perform field balance, trim balancing, as per related balancing grade to reduce residual unbalance in coupling to overcome high 1x vibration. Normally, trim balancing holes are provided in turbomachinery coupling as shown in picture. Coupling misalignment refers to the improper positioning of connected shafts, categorized into three primary types: angular, radial, parallel, and axial gap misalignment. These, combined with vertical or horizontal planes, often result in combined misalignment. Proper alignment reduces vibration, bearing wear, and energy loss. Coupling misalignment cause high vibration. A typical spectrum is shown in this slide. For sliding the coupling spacer/tubular shaft, the location of motor magnetic center, must be known prior to starting the alignment. One should not assume that it is located in the middle of the total motor shaft axial travel. DBSE plus margin. The margin must be maintained while positioning the coupling spacer. Refer GA as supplied by original equipment manufacturer. A high value of misalignment kills the intent of flexible coupling and causes severe cyclic stress. Cardan shaft, universal joints are also susceptible to misalignment. If there is very high vibration in connected component, some part of vibration may be transferred into adjacent component even coupling is flexible. A long or heavy spacer tube extends the coupling's center of gravity, CG, away from the machine's supporting bearing, resulting in a large overhung moment. This configuration, often used to allow for maintenance without moving the driver or driven equipment, spacer-type couplings, introduces several risks, primarily centered on rotor dynamics. Excessive overhung mass/moment can shift the machine's lateral critical frequency closer to the operating speed range, causing high vibration. The weight of the spacer can create significant shaft deflection. Large gas and steam turbines are ideal applications where the diaphragm coupling's diaphragm can bolt directly to the turbine flange, thereby giving the best center of gravity location relative to the turbine bearing. In summary, the use of large spacer couplings requires careful engineering calculation of the bending and torsional moments acting on the shaft ends, particularly for high-speed machinery. The larger coupling flanges with higher number of bolt heads cause significant amounts of windage, resulting in frictional heating of the air in the coupling guard. Coupling guard volume, net cooling airflow, and clearance between the flanges and the guard internal wall became important factors. An improperly designed coupling guard results in unacceptably high coupling guard surface and internal coupling temperatures. Further, closed radial clearances effectively create separated hot volumes inside the guard. Negative pressures are created occasionally in the vicinity of machinery seals, causing oil to be sucked in the coupling enclosure. To prevent oil mist getting transferred due to vacuum created, a baffle plate placed between the end of the coupling and the seal area of the machine. The presence of this plate virtually eliminated the effects of the vacuum produced by the rotation of the coupling. The temperature rise inside coupling guard may cause bow effect in spacer, causing high 1x vibration. Coupling hub slip torque defines the maximum torque a hub can transmit before slipping on the shaft, is calculated based on following parameters such as coefficient of friction between hub and shaft, contact pressure, the pressure between the hub and shaft, contact area based on shaft diameter and hub engagement length. Similarly, coupling hub pulling force also follow the same formula with same parameters. Shaft couplings directly influence lateral critical speed by affecting the total rotor mass, stiffness, and overhung moment, distance from bearing to center of gravity. A heavier or less stiff coupling generally lowers the lateral critical speed, while minimizing the overhung moment and optimizing coupling stiffness can raise it, improving stability. Key effects of couplings on lateral critical speed are overhung moment. The distance between the bearing and the coupling center of gravity is critical. A larger overhung moment reduces the lateral critical speed, whereas moving the coupling closer to the bearing increases it. Mass and inertia. The coupling adds mass to the rotor system, typically decreasing the natural frequency and, therefore, the lateral critical speed. Stiffness. The coupling is often the least stiff component, allowing for tuning the drivetrain's rotor dynamics. Increasing the coupling stiffness can help raise the critical speed, while a flexible coupling may lower it. There are specified circumstances in which the train lateral analysis can be considered. First, when coupling spacer natural frequency is within the region shown as figure in API TR 684 as train lateral recommended. Here we can see the coupling hub weight and half of spacer weight to be considered in journal load for the bearings nearest to coupling hub. Second, the coupling is not of the flexible spacer type. These situations would include hard-coupled turbomachinery typically consisting of a single fixed joint. There is no requirement based on coupling spacer length. Axial natural frequency of a coupling is the resonant frequency at which it oscillates along its rotational axis. Metal flexing couplings often exhibit significant axial vibration when the excitation frequency matches the coupling's natural frequency. A mass-elastic diagram for analyzing the axial natural frequency of a flexible disc pack coupling simplifies the physical system into a mass spring mass model, enabling the calculation of the resonant frequency of the spool piece or center member between the driving and driven equipment. Mass elastic diagram model for a standard double flexing disc coupling. The axial system is usually modeled as masses of the driving and driven hubs and attached shaft inertia. Intermediate mass represents the center spacer/spool piece. Stiffnesses represent the axial stiffness of the disc packs, acting as springs between the hubs and the spool. The most fundamental representation is a 3-degree of freedom system. Torsional vibration mode shapes represent the relative angular displacement, twisting, along a shaft system at specific natural frequencies, showing where the shaft rotates most, antinodes, and where it remains stationary nodes. They are critical for identifying resonant conditions, with the first mode showing the lowest frequency and typically the highest amplitude, often involving flexible couplings. Torsional vibration causes significant stress, overheating, and premature failure in couplings by introducing alternating torque spikes, which can lead to disc pack shims deformation, fatigue-induced fractures. These vibrations often cause catastrophic, rapid failures if the system operates near a torsional natural frequency. Equivalent stiffness of machinery unit is influenced by stiffness of shafts and connecting coupling. Since due to performance requirement we cannot change the design of driver and driven, only option lies in changing the coupling stiffness. The stiffness is based on coupling geometry such as diameter of spacer and length of spacer. Another option can be costly, which is to change the material of construction of coupling, such as to titanium, to change the shear modulus. Torsional vibration in a train can be controlled using a larger spacer tube in coupling, which lowers torsional stiffness of coupling and shifts the torsional natural frequency. Oppositely, a stiffer coupling with material like titanium can also shift the train torsional frequency. A softer coupling using elastomeric-type whole-set damper coupling also isolates the source of torsional vibration to affected component. Within 5 megawatts of drive with a synchronous motor, a hydrodynamic fluid coupling also can isolate the source of torsional vibration to affected component. A grid coupling also can work well in case of torque overload by twisting the grid spring. If it breaks, the unit is decoupled and major components are protected. Torque-limiting couplings shown top right are mechanical safety devices designed to protect machinery from damage caused by excessive torque or mechanical overload by disengaging or slipping when a preset torque threshold is exceeded. Idling adapter is used when undertaking a solo run of unit without coupling spacer and contract coupling hub is not available. The moment simulator is a simple, dummy hub design to match the half weight and center of gravity of the coupling. The moment simulator is mounted in place of the hub/membrane assembly. Motor vendor was called to site and field balancing was done on motors. After field balancing of motor-coupled runs were conducted, which showed up with high vibration on pinion side. As the compressor vibration reports were well below the acceptance criteria at test bed, coupling unbalance was under scrutiny. It was found that the reason of unbalance was mismatch in coupling set, and the field balancing was proposed to solve this issue. Furthermore, it was understood that field balance would be at speed while shop balance is at a low RPM. Match marking shall be done by etching on full set to eliminate any chances of possible error during dismantling and assembly in case any maintenance activity is carried out by operations in future. Before the commencement of trim balancing activity, it was ensured that XY probes and alarm and trip values for complete train should not be compromised during balancing activity. 2. Key phaser shall be calibrated. 3. The added weights must be adequately secured so that there is no chance of fly-off, which can be lethal. For during balancing, plots and spectrum should be taken out from System 1 and kept as snapshot if possible, which should be circulated and kept as record. 5. At least 3 readings should be taken for complete train vibration for repeatability check after balancing. The person should be certified to carry out the work. After successful activity of field balancing using trim holes provided, vibration came under acceptance criteria. For deep dive into the subject, I recommended to refer dedicated books on couplings and machine design. There are many literatures and case studies available for Texas A&M symposiums, ASME publications, Turbomachinery magazine, etc. as well. Thank you for watching this video. Hope this has benefited you to an extent. It is our constant endeavor to share relevant technical knowledge with machinery engineers involved in design, installation, and reliable operation of rotating machinery. Subscribe to the YouTube channel and visit our website for technical repository.